We discuss the continuity of a function at a number. We say that a function f is continuous at a number a if it satisfies the following conditions. First, f of a exists. That means that a is in the domain of the function f and that its function value f of a exists. Second, the limit of f of x as x approaches a exists. And third, the limit of f of x as x approaches a is equal to its functional value. So if any of the above conditions fails, we say that the function f is discontinuous at the number a. Actually, we only have to show that the limit of f of x as x approaches a is equal to its function value f of a to say that the function is continuous at the number a. We take on the following example. Given a function f defined by f of x equal to x squared minus 2x plus 1, we determine the continuity of f at the number 2. The function f can be written as y equal to x minus 1 quantity squared, since x squared minus 2x plus 1 is a perfect square trinomial. And it is clear that the graph of the function is a parabola with vertex at 1, 0 and opening upward. Now we want to find the continuity of the function at x equal to 2. So we start with the function value. F of 2 is equal to 2 squared minus 2 times 2 plus 1 equal to 1. So we determine the function value by simply substituting 2 to all the x's in f. So the function value, f of 2 is equal to 1. And that represents the point 2, 1. In the graph of f, it represents the point 2, 1. Next, we determine the limit of f of x as x approaches 2. So we evaluate the limit of x squared minus 2x plus 1 as x approaches 2. By substitution method, that becomes 2 squared minus 2 times 2 plus 1 equal to 1. So as you have observed, the function value f of 2 and the limit of f as x approaches 2 are equal. So we say that the function f is continuous at x equal to 2. Looking at the graph of the parabola, observe that the graph is continuous as it passes through the point 2, 1. So if there is no break in the graph of the function at the point 2, 1, we can say that, graphically speaking, the function is continuous at x equal to 2. Next, given the function g defined by g of x equal to the absolute value of x minus 2 if x is not equal to 2, and 1 if x is equal to 2, is g continuous at the number 2? So first, the function value g of 2. When x is equal to 2, it is clear that g is equal to 1. So g of 2 is equal to 1. Next, we evaluate the limit of g of x as x approaches 2. So right and left of x equal to 2, g of x is equal to the absolute value of x minus 2. But to solve for the two-sided limit as x approaches 2, we need to evaluate the one-sided limits as x approaches 2 from the left and as x approaches 2 from the right. Remember that the definition of the absolute value x is equal to x if x is greater than or equal to 0 and negative of x if x is less than 0. So for the absolute value of x minus 2, that is equal to x minus 2 if x minus 2 is greater than or equal to 0, and the negative of x minus 2 if x minus 2 is less than 0. So if x is approaching 2 from the left, that means that x is less than 2. And for x less than 2, that falls under x minus 2 less than 0. Our absolute value x minus 2 is the negative of x minus 2. Again, since we are evaluating the left-hand limit as x approaches 2 from the left, we need x's that are less than 2. And x's less than 2 are in the interval x minus 2 less than 0. And for that, the absolute value is the negative of x minus 2. So hence, we evaluate the limit of x minus 2 or 2 minus x, no? The negative of x minus 2 or 2 minus x as x approaches 2 from the left, which is equal to 0. Then we evaluate the right-hand limit. As x approaches 2 from the right means that x is greater than 2. And for x greater than 2, or x minus 2 is greater than or equal to 0, the absolute value is x minus 2. So evaluate the limit of x minus 2 as x approaches 2 from the right equal to 0. And as you can see, both one-sided limits are equal. Hence, we say that the limit of g of x as x approaches 2 is equal to the common one-sided limit 0. But observe also that the function value g of 2 and the limit are not equal. Hence, we say that the function g is discontinuous at x equal to 2. Observe that in the graph of g of x, there is a break in the graph at x equal to 2. For x equal to 2, it jumps to the point 2, 1. Alright? So, if we are to draw the function if we can draw the function without lifting the pen as it goes through the point where x is 2, the function is continuous. But in here, you should observe that if we are to draw the function or the graph, we need to lift up our pen in order to include the point 2, 1, because 2, 1 is in the graph. No? So we cannot draw the graph continuously without lifting our pen at x equal to 2. So hence, the function is discontinuous at x equal to 2. For our next example, let us consider the function h defined by h of x equal to the square root of x minus 2 if x is greater than or equal to 2, and x squared minus 4 if x is less than 2. We determine the continuity of g at the number 2. First, we find the function value h of 2. So, x is equal to 2 is in the interval x greater than or equal to 2. So, we substitute 2 to x in the square root of x minus 2. That gives us 0. Next, we evaluate the limit of h of x as x approaches 2 from the left. Because the intervals involved are 0 to 2, or rather negative infinity to 2, and 2 to positive infinity, and we want to find the continuity at 2, there is a need of evaluating the right and the left hand limits. So, as x approaches 2 from the left, meaning x is less than 2, we will consider x squared minus 4. So, we evaluate the limit of x squared minus 4 as x approaches 2 from the left, which is equal to 0. Then we evaluate the right-hand limit as x approaches 2, meaning x is greater than 2. And for all x is greater than 2, our h is the square root of x minus 2. For x is greater than 2, h is square root of x minus 2. Evaluating the limit of the square root of x minus 2 as x approaches 2 from the right, is the square root of 2 minus 2, or the square root of 0, which is 0. So, the left-hand limit and the right-hand limit as x approaches 2 are both equal to 0. So we say that the two-sided limit h of x as x approaches 2 exists and is equal to 0. So we just check if the function value and the limit are equal, and obviously they are. So we say that h is continuous at x equal to 2. Observe that when you graph the piecewise function, no, for x greater than or equal to 2, that is the square root of x minus 2. So that is actually the upper half of a parabola with axis horizontal. Since it is the positive square root, it is the upper half of the parabola. Alright? And then for all x's less than 2, it is x squared minus 4, which is actually a parabola with vertex at 0, negative 4, terminating at x equal to 2. So the endpoint of the parabola, the right endpoint of the parabola, is open at 2, 0. But since the left end of the graph of square root of x minus 2, that is at x equal to 2, is 2, 0, then it makes the function continuous at x equal to 2. Though the point 2, 0 is excluded in the parabola, it is included, on the other hand, in the graph of square root of x minus 2. So there is continuity at x equal to 2. We consider another piecewise function t defined by t of x equal to 2 minus x if x is less than or equal to negative 1, and 1 if x is greater than negative 1. Is t continuous at negative 1? Alright? So 2 minus x is a line, so is t of x equal to 1. Alright? So the function value, t of negative 1, is 2 times the negative of negative 1. Negative 1 is contained in the interval x less than or equal to negative 1. So to find the function value when x is negative 1, we substitute negative 1 to x in 2 minus x, and that gives us 3. Since, again, we are testing the continuity of t at negative 1, where negative 1 is an endpoint of the intervals involved, negative infinity to negative 1 and negative 1 to positive infinity, there is a need of evaluating the one-sided limits. So as x approaches negative 1 from the left, meaning less than negative 1, we take on the limit of 2 minus x as x approaches negative 1. And that is equal to 2 minus negative 1, or 3. As for the right-hand limit, as x approaches negative 1, that means that x is greater than negative 1. And for x greater than negative 1, t of x is 1. And the limit of 1 is, of course, equal to 1. See that the left-hand limit and the right-hand limit are not equal. So we say that the two-sided limit of t of x as x approaches negative 1 does not exist. So since the limit does not exist, we can conclude that the function t is discontinuous at negative 1 from the graph of t. As the graph goes to the point where x is negative 1, there is a break in the graph of the function. Hence, it is discontinuous at negative 1. Let us now consider the function f defined by f of x equal to 1 over x minus 3 if x is not equal to 3, and negative 1 if x is equal to 3. We check on the continuity of f as at the number 3. So f of 3, when x is 3, f of x is negative 1. So the function value at x equal to 3 is negative 1. Next, left and right of 3, we evaluate the limit. So we take on the limit of 1 over x minus 3 as x approaches 3 from the left, meaning less than 3. So x minus 3 will approach 0 through negative values because x is less than 3. A number less than 3 minus 3 is of course negative. So 1 over 0 through negative values is negative infinity. As for the right-hand limit, that means that x is greater than 3. So if we are to evaluate the limit of 1 over x minus 3, where x is greater than 3, the denominator will approach 0 through positive values. And 1 divided by a very small number that is positive will yield positive infinity. So strictly speaking, there is no limit as f of x, or rather as x approaches 3. So we have infinite limits as x approaches 3. As x approaches 3 from the left, it is negative infinity, and as x approaches 3 from the right, it's positive infinity. So obviously, the function is discontinuous at 3. Looking at the graph, no, see that there is a vertical asymptote at x equal to 3, but the function nonetheless is defined when x is equal to 3, that is equal to negative 1. So the point 3 comma negative 1 is part of the graph of the function f. And obviously the graph cannot be drawn without lifting the pen as it goes through the point 3 comma negative 1. So obviously it is discontinuous at x equal to 3. So far we have encountered several functions that are discontinuous at a specific number. So we discussed the two different types of discontinuity. The first one is removable and the other is essential discontinuity. These two graphs here are examples of functions with removable discontinuity. In here, observe that f has a limit as x approaches a from the right or from the left. It converges at this point. But observe that the function is defined at a, comma, 0. The function value of f at x equal to a is actually 0 because the point is on the x-axis. All right? Now we call this as a removable discontinuity. Why? Because by redefining the function, by plugging the hole here in the graph, by this point, a comma 0, if we are to move that point in order to fill up the space here, it will make the function continuous. So that is why it is removable. We redefine the function, and instead of f of a equal to 0, our f of a will be this point. Whatever the y value here is, whatever the limit of f is, we equate that to the function value f of a. The other example here is the function f defined by the absolute value of x minus 2 if x is not equal to 2 and 1 if x equal to 2. So the right hand and the left hand limit both exist equal to 0, but the function value is 1. When x is 2, f of 2 is 1. Again, we can remove the discontinuity by moving this point 2, 1 to 2, 0 to fill up the space here. The open circle here can be closed by plugging in the point. So we just redefine the function to make the function continuous at that number 2. To illustrate essential discontinuity, we have these two examples. Notice that in here, the two-sided limit does not exist. All right? There is no way we can redefine the function to remove the discontinuity. If it is just a mispoint, it will be a removable discontinuity. But in here, we have to move this entire graph to this point in order to make the function continuous. And we cannot do that. No, we cannot redefine the function in a way that this entire section of the graph will be connected to the right endpoint of the graph of f. All right. So the function here is discontinuous, and the type of discontinuity is essential. Why? Because the limit does not exist. It may have a function value, but if the limit does not exist, then automatically the discontinuity is an essential one. And to further classify the discontinuity here, we refer to this type of discontinuity as a jump discontinuity. From one graph, it jumps to the other segment of the graph. While this one is called an infinite discontinuity. It's also an essential discontinuity and further classified into infinite discontinuity. Why? Because there is infinity involved as regards to the limit of g. The limit of g as x approaches a from the right is positive infinity, and the limit of g as x approaches a from the left is negative infinity. So if there is an infinite limit involved, that is an essential discontinuity, called also as an infinite discontinuity. Given the graphs of three discontinuous functions, you classify the discontinuity as to whether it is a removable discontinuity or an essential discontinuity. And if it is an essential discontinuity, further classify it as a jump discontinuity or an infinite discontinuity. So I'm giving you a few moments to answer the type of discontinuity for the given functions. All right, so we check on your answer. For the first one, it is an essential discontinuity, a jump discontinuity. The second one is a removable discontinuity, and third is an essential discontinuity, an infinite discontinuity. Let us now go to our final example about continuity. Given the function f defined by f of x equal to 3x minus 1 if x is less than 3, 2 if x is equal to 3, 11 minus x if x is greater than 3. Is f continuous at 3? If not, indicate the type of discontinuity. So given this piecewise function, we determine the continuity of that function at x equal to 3. If there is discontinuity involved, we state the type of discontinuity. So the first condition is that it must have a function value at x equal to 3. So f of 3 is equal to 2. From the definition of f, it says that if x is 3, then f is 2. So 2 is the function value at x equal to 3. Since the endpoint of the intervals involved is 3, one of the endpoints of the intervals involved is 3, then we check the one-sided limits. So the limit of f of x as x approaches 3 from the left is equivalent to x less than 3, 3x minus 1. And the limit of 3x minus 1 as x approaches 3 is equal to 8. The right-hand limit as x approaches 3 means that x is greater than 3. And for x greater than 3, your f is 11 minus x. So 11 minus 3 is 8. So the right and left-hand limits are both equal to 8. Hence, we say that the two-sided limit of f as x approaches 3 is 8. But Observe that the function value f of 3, which is 2, is not equal to the limit of f of x as x approaches 3. So we say that the function is discontinuous at 3. Now let us draw the graph of the function. So for x less than 3, it is the line 3x minus 1. And for x greater than 3, it is the line 11 minus x. Observe that in both intervals, x less than 3 and x greater than 3, 3 is not included. Hence, we indicate that point 3, 8 with an open circle. Indicative that that point is not included in the graph. But it says that x is equal to 3, or when x is 3, your f is 2. So it is this point 3, 2, which is part of the graph of the function. The point 3, 8 is excluded. Instead, we have the point 3, 2. And the type of discontinuity here is a removable discontinuity. Why? Because by taking off the point 3, 2 and plugging it in to the point 3, 8, the open circle here, it will make the function continuous at x equal to 3. So we redefine the function as 3x minus 1 if x is less than 3, and when x is 3, it is equal to 8. So before it's equal to 2, now we redefine it to be equal to 8. And for x greater than 3, it is 11 minus x. Another way of redefining this function is by setting 3x minus 1 if x is not just less than 3, but also equal to 3, because it will also give us the function value of 8. As for the exercises about asymptotes and continuity, you work on the following numbers. Number 1, you find the asymptotes, if any, both horizontal and vertical, for the given function and sketch its graph, where f of x is equal to 2x squared all over x squared minus 3x minus 4. Second one, for the given graph of a certain function f, state the type of discontinuity at the following indicated numbers. And third, given a function g defined by the square root of x squared minus 4 if x is less than negative 2, x plus 2 if x is between negative 2 and 2, inclusive of the endpoints, and 1 over x minus 2 if x is greater than 2. So you answer the question, is g continuous at negative 2 for letter A and 2 for letter B? And you are also required to do the graph of the function g.